So hello guys, welcome back to another video on wave optics. In this video we are going to try to prove the law of reflection, that is angle of incidence is equal to angle of reflection, but with the help of wave optics, that is by using Huygen's principle. It's quite important to understand this derivation because it will kind of prove the validity of wave optics. So let's go ahead to understand this basic derivation. Okay. So this is a figure that I've got. Figures form the most integral part in each and every of your derivation. So make sure that you draw them clearly. So let's understand and analyze the figure first. After that, we'll be moving on to a simple geometry problem. This is incoming ray I1, this is incoming ray I2. Both are coming and being incident on a plane, smooth, reflecting surface. Clear? And this is a plane wavefront. We must always remember that wavefronts and rays of light always make a 90-degree angle between them, never any other angle. Okay? So wavefronts and rays always make 90-degree angles between them. Considering this point, we'll move ahead. So the ray I1 comes and strikes the reflecting surface O, but by that time the ray I2 has only moved up to the point C. Got it? By the time I1 strikes O, I2 would have only moved up to C, because I2 has to clearly travel a longer distance as compared to I1. Cool. So let's apply the same after reflection. And by the time I2 strikes the point A, that is on the surface, I1 would have traversed a distance OB. That's because I1 is kind of ahead in time of I2. So it must have traveled an extra distance. That's it. That's about these perpendiculars. Let's now move on to these angles, these weird markings that I've done here. We'll be considering the angle of incidence up here and the angle of reflection up here. Let's see the angle of incidence here. We know that angles in lines and planes, lines and wavefronts, lines and wavefronts always make a 90-degree angle between them. Therefore, if this angle is I, this angle must be 90 minus I. By simple geometry, because normals are always perpendicular to the surfaces, if this angle is 90 minus I, this angle must be I. Similarly, if this angle is R, then this angle must also be R. If you're a little bit confused, just pause the video, rewind the video, watch it at a slower pace, and then you'll get a grasp of it. Okay? So let's now move ahead. Let's consider the triangles OCA and triangles OBA. We'll be considering these two pairs of triangles to show them that they are congruent. Let's see. So in triangles OCA and OBA, what we observe is that OA is a common base. Okay, cool. And we also observe that OBA is obviously equal to angle OCA, which is equal to 90 degrees, and OB is equal to AC. So by SAS congruency condition, these two triangles right here are obviously congruent, and by the rule of corresponding parts of congruent triangles, we can clearly say that angle of incidence is equal to angle of reflection. Why? Because considering the triangle OCA, the angle of incidence is this cornerish angle right here, and considering the triangle OBA, the angle of reflection is the cornerish angle right here. So we can clearly see that angle of incidence is equal to angle of reflection, and hence we can easily prove by Huygen's principle that angle of incidence is equal to angle of reflection, which is a basic law of reflection. Thus, in this video, we have proved angle of incidence is equal to angle of reflection with the help of Huygen's principle, which kinda proves the validity of wave optics up to a certain extent. So let me give you a quick snapshot of this whole derivation once, so that you can quickly take a screenshot of it if you really want to. So here you go. You first basically proved both the triangles as congruent, and then you moved on to say that angle of phi is equal to angle of r by CPCT. So that's it for this video, guys. Remember always, the diagrams form the integral part of your derivations, so always draw them with care. Thank you, guys.